Hashing a randomized implementation of dictionaries. Randomization has also proved to be a powerful technique in the design of data structures. Here we discuss perhaps the most fundamental use of randomization in this setting, a technique called hashing that can be used to maintain a dynamically changing set of elements. In the next section, we will show how an application of this technique yields a very simple algorithm for a problem that we saw in Chapter 5, the problem of finding the closest pair of points in the plane. The problem: one of the most basic applications of data structures is to simplify maintain a set of elements that changes over time. For example, such applications could include a large company maintaining the set of its current employees and the contractors, a news indexing services recording the first paragraphs of news articles it has seen coming across the newswire, or a search algorithm keeping track of the small part of an exponentially large search space that it has already explored. In all these examples, there is a universe U of possible elements that is extremely large, the set of all possible people, all possible paragraphs, say up to some character length limit, or all possible solutions to a computationally hard problem. The data structure is trying to keep track of a set S, which is a subset equals to U, whose size is generally a negligible fraction of U, and the goal is to be able to insert and delete elements from S and quickly determine whether a given element belongs to S. We will call a data structure that accomplishes this a dictionary. More precisely, a dictionary is a data structure that supports the following operations. Make dictionary. This operation initializes a fresh dictionary that can maintain a subset S of U. The dictionary starts out empty. Insert of U adds element little u in capital U, the universal set, to the set S. In many applications, there may be some additional information that we want to associate with U. For example, U may be the name or ID number of an employee, and we want to also store some personal information about this employee, and we will simply imagine this being stored in the dictionary as part of the record together with U. So, in general, when we talk about the element U, we really mean U and any additional information stored with U. Delete of U removes element U from the set S if it is currently present. Lookup of U determines whether U currently belongs to S. If it does, it also retrieves any additional information stored with U. Many of the implementations we've discussed earlier in the book involve most of these operations. For example, in the implementation of the BFS and the DFS graph traversal algorithms, we needed to maintain the set S of nodes already visited. But there is a fundamental difference between those problems and the present setting, and that is the size of U. The universe U in BFS or DFS is the set of nodes V, which is already given explicitly as part of the input. Thus, it is completely feasible in those cases to maintain a set S which is subset equals to S as we did there, defining an array with the size of U positions, one for each possible element, and then setting the array position for U equal to 1 if U is in S and equals to 0 if U is not in S. This allows for insertion, deletion, and lookup of elements in a constant time per operation by simply accessing the desired array entry. Here, by contrast, we are considering the setting in which the universe U is enormous, so we are not going to be able to use an array whose size is anywhere near that of U. The fundamental question is whether, in this case, we can still implement a dictionary to support the basic operations almost as quickly as when U was relatively small. We now described a randomized technique called hashing that addresses this question. While we will not be able to do quite as well as the case in which it is feasible to define an array over all of U, hashing will allow us to come quite close. Designing the data structure. As a motivating example, let's think a bit more about the problem faced by an automated service that processes breaking news. Suppose you are receiving a steady stream of short articles from various wire services, weblog postings, and so forth, and you are storing the lead paragraph of each article, truncated to at most 1000 characters. Because you're using many sources for the sake of full coverage, there's a lot of redundancy. The same article can show up many times. When a new article shows up, you'd like to quickly check whether you've seen the lead paragraph before. So, a dictionary is exactly what you want for this problem. The universe U is a set of all streams of length at most 1000, or of length exactly 1000 if we pad them out with blanks. And we are maintaining a set S, which is a subset equals to U, consisting of streams, i.e. lead paragraphs that we've seen before. One solution would be to keep a linked list of all paragraphs and scan this list each time a new one arrives. But a lookup operation in this case takes time proportional to the size of S. How can we get back to something that looks like an array-based solution? Hash functions. The basic idea of hashing is to work with an array of the size of S rather than one comparable to the astronomical size of U. Suppose that we want to be able to store a set S of size up to n. We will set up an array H of size n to store the information and use a function H which maps the universal U to the set 0, 1, 2, 3 until n minus 1 that maps elements of U to array positions. We call such a function H a hash function and the array H a hash table. Now if we want to add an element U to the set S, we simply place U in position H of U of the array H. In the case of storing paragraphs of text, we can think of H dot as computing some kind of a numerical signature or checksum of the paragraph U, and this tells us the array position at which to store U. This would work extremely well if, for all distinct U and V in our set S, it happened to be the case that H of U is not equals to H of V. In such a case, we could look up U in a constant time. When we check array position H of U, it would either be empty or would contain just U. In general, though, we cannot expect it to be this lucky. There can be distinct elements U, V in S for which H of U is equal to H of V. We will say that these two elements collide since they are mapped to the same place in H. There are a number of ways to deal with the collisions. Here we will assume that each position H of I of the hash table stores a linked list of all elements U in S with H of U is equal to I. The operation lookup of U would now work as follows. Compute the hash function H of U. Scan the linked list at position capital H of U to see if a U is present in this list. Hence, the time required for lookup of U is proportional to the time to compute H of U plus the length of the linked list at capital H of U. And this later quantity, in turn, is just the number of elements in S that collide with U. The insert and the delete operations work similarly. Insert adds U to the linked list at a position capital H of U and delete scans this list and removes U if it is present. So now the goal is clear. We'd like to find a hash function that spreads out the elements being added so that no one entry of the hash table capital H contains too many elements. This is not a problem for which worst-case analysis is very informative. Indeed, suppose that the capital U, the size of U, is greater than or equals to n squared. We are imagining applications when it's much larger than this. Then, for any hash function h that we choose, there will be some set S of n elements that all map to the same position. In the worst case, we will insert all the elements to this set And then our lookup operations will consist of scanning a linked list of length n. Our main goal here is to show that randomization can help significantly for this problem. As usual, we won't make any assumptions about the set of elements as being random. We will simply exploit randomization in the design of the hash function. In doing this, we won't be able to completely avoid collisions, but we can make them relatively rare enough, and still the lists will be quite short. Choosing a good hashing function. We've seen that the efficiency of the dictionary is based on the choice of the hash function h. Typically, we will think of u as a large set of numbers and then use an easily computable function h that maps each number u in capital U to some value in the smaller range of integers 0, 1, 2, 3, and so on until n minus 1. There are many simple ways to do this. We could use the first or last few digits of u, or simply take u modulo n. While these simple choices may work well in many situations, it is also possible to get large numbers of collisions. Indeed, a fixed choice of a hash function may run into problems because of the types of elements u encountered in the application. Maybe the particular digits we used to define the hash function encode some property of u, and hence maybe only a few options are possible. Taking u modulo n can have the same problem, especially if n is a power of 2. To take a concrete example, suppose we used a hash function that took an English paragraph, used a standard character encoding scheme like AC2 to map it to a sequence of bits, and then kept only the first few bits in this sequence. We'll expect a huge number of collisions at the array entries corresponding to the bit streams that encoded common English words like THEV, while vast portions of the array can be occupied only by paragraphs that begin with streams like QXF and hence will be empty. A slightly better choice in practice is to take u modulo p, u mod p for a prime number p that is approximately equal to n. Well, in some applications, this may yield a good hashing function. It may not work well in all applications, and some primes may work much better than others. For example, primes very close to powers of 2 may not work so well. Since hashing has been widely used in practice for a long time, there is a lot of experiences with what makes for a good hash function, and many hash functions have been proposed that tend to work well empirically. Here we would like to develop a hashing scheme where we can prove that it results in efficient dictionary operations with high probability. The basic idea, as suggested earlier, is to use randomization in the construction of H. First, let's consider an extreme version of this for every element little u in the universal set U. When we go to insert u into S, we select a value h of u uniformly at random in the set among 0, 1, 2, 3 until n minus 1, independently of all previous choices. In this case, the probability that two randomly selected values h of u and h of v are equal and hence cause a collision is quite small. 13.22. With this uniform random hashing scheme, the probability that two randomly selected values, h of u and h of v, collide, that is, that h of u is equals to h of v, is exactly 1 over n. Proof. Of the n squared possible choices for the pair of values, h of u, h of v, all are equally likely, and exactly n of these choices results in a collection. However, it will not work to use a hash function with independently random chosen values. To see why, suppose we inserted u into S and then later want to perform either delete of u or lookup of u. We immediately run into the where did I put it problem. We will need to know the random value h of u what we used, so we will need to have stored the value h of u in some form where we can quickly look it up, but this is exactly the same problem we were trying to solve in the first place. There are two things that we can learn from 13.22. First, it provides a concrete basis for the intuition from practice that hash functions that spread things around in a random way can be effective at reducing collisions. Second, and more crucial for our goals here, we will be able to show how a more controlled use of randomization achieves performance as good as suggested in 13.22, but in a way that leads to an efficient dictionary implementation. Universal classes of hash functions. The key idea is to choose a hash function at random, not from the collection of all possible functions into the closed interval between 0 and n minus 1, but from a carefully selected class of functions. Each function h in our class of functions fancy H will map the universe capital U into the set 0, 1, 2, 3 until n minus 1. And we will design it so that it has two properties. First, we'd like it to come with the guarantee from 13.22. That is, for any pair of elements U and V in the universal set, capital U, the probability that a randomly chosen H in fancy H satisfies H of U equals to H of V is at most 1 over n. We say that the class fancy H of functions is universal if it satisfies this first property. Thus, 13.22 can be viewed as saying that the class of all possible functions from U into the set 0, 1, 2, 3 until n minus 1 is universal. However, we also need fancy H to satisfy a second property. We will state this slightly informally for now and make it more precise later. Each H in fancy H can be compactly represented, and for a given little h in fancy H and little u in fancy U, we can compute the value H of U efficiently. The class of all possible functions failed to have this property. Essentially, the only way to represent an arbitrary function from fancy U into the set 0, 1, 2, 3 until n minus 1 is to write down the value it takes to every single element of fancy U. In the remainder of this section, we will show the surprising fact that there exist classes fancy H that satisfy both of these properties. Before we do this, we first make precise the basic property we need from a universal class of hash functions. We argue that if a function h is selected at random from a universal class of hash functions, then in any set S which is a subset of U of size at most n, and any little u in fancy U, the expected number of items in S that collide with U is a constant. 13.23. Let fancy H be a universal class of hash functions, mapping a universe U to the set 0, 1, 2, 3 until n minus 1. Let S be an arbitrary subset of U of size at most n, and let U be any element in fancy U. We define capital X to be a random variable equal to the number of elements little s in fancy S, capital S, for which H of S is equals to H of U, for a random choice of hash functions little h in fancy H. Here S and U are fixed, and the randomness is in the choice of little h in fancy H. Then the expected values of X is less than equals to 1. Proof: for an element little s in capital S, we define a random variable xs that is equals to 1 if h of s is equals to h of u and equal to 0 otherwise. We have the expectations of xs is equals to the probability such that xs is equals to 1, which is less than equals to 1 over n, since the class of functions is universal. Now x is equals to the summations of xs, summing for all little s in capital S, and so by linearity of expectation, we have expectations of x is equals to the summations of expectations of xs, summing for all little s in capital S, which is less than equals to the size of S times 1 over n, which is less than or equals to 1. Designing a universal class of hash functions. Next, we will design a universal class of hash functions. We will use a prime number p, which is approximately n, as the size of the hash table h. To be able to use integer arithmetic in designing our hash functions, we will identify the universe with vectors of the form x equals to x1, x2, x3, and so on until xr for some integer r, where 0 is less than or equals to xi less than p for each I. For example, we can first identify u with integers in the range between the 0 and n minus 1 for some n, and then use the consecutive blocks of the floor functions of log p bits of u to define the corresponding coordinates xi. If u is a subset equals to the range between 0 and n minus 1, then we will need a number of coordinates r, which is approximately be equals to the values of a log of capital N divided by log of little n. Let A be the set of all vectors of the form A equals to A1, A2, A3, and so on until AR, where AI is an integer in the range between 0 and p minus 1 for each I equals to 1, 2, 3 until R. For each A, which is in fancy A, we defined the linear function HA of x is equals to the summations of AI times xi, summing with index I starting from 1 to R, then modulo p. This now completes our random implementations of dictionaries. We defined the family of hash functions to be fancy h equals to the set HA such that little a is in capital A. To execute make dictionary, we choose a random hash function from fancy h. In other words, we choose a random vector from A by choosing each coordinate uniformly at random. And from the function HA, note that in order to define A, we need to find a prime number p which is greater than or equals to n. There are methods for generating prime numbers quickly, which we will not go into here. In practice, this can also be accomplished using a table of known prime numbers, even for relatively large n. We then use this as the hash function with which to implement insert, delete, and lookup. The family fancy h, which is equals to the set HA such that little a is in capital A, satisfies a formal version of the second property we were seeking. It has a compact representation, since by simply choosing and remembering a random little a which is in capital A, we can compute HA of u for all elements little u in fancy u. Thus, to show that H leads to an efficient hashing-based implementation of dictionaries, we just need to establish that H, fancy H, is a universal family of hash functions. Analyzing the data structure. If we are using a hash function HA from the class fancy H that we've defined, then a collision HA of x is equals to HA of y defines a linear equation modulo the prime number p. In order to analyze such equations, it's useful to have the following cancellation law. 13.24. For any prime number p and any integer z which is not equal to 0 modulo p, and any two integers alpha beta if alpha times z is equals to beta times z under the modulo p, then alpha is equals to beta modulo p. Proof: suppose that alpha z is equals to beta z modulo p. Then, by rearranging terms, we get z times alpha minus beta is equals to 0 modulo p, and hence z times alpha modulo beta is divisible by p. But z is not equals to 0 modulo p, so z is not divisible by p. Since a p is prime, it follows that alpha minus beta must be divisible by p. Thus, alpha is equals to beta modulo p as claimed. We now use this to prove the main result in our analysis. 13.25. The class of linear function fancy h defined above is universal. Prove that x equals to x1, x2, x3, and so on to xr, and y equals to y1, y2, y3, until y are to be two distinct elements of U, we need to show that the probability of HA of x is equals to HA of y for a randomly chosen little a in capital A is at most 1 over p. Since x is not equals to y, then there must be an integer, an index j, such that xj is not equals to yj. We now consider the following way of choosing the random vector, little a in capital A. We first choose all the coordinates ai, where I is not equals to j. Then, finally, we choose coordinate aj. We will show that regardless of how all the other coordinates ai were chosen, the probability of HA of x is equals to HA of y taken over the final choice of aj is exactly 1 over p. It will follow that the probability of HA of x is equals to HA of y over the random choice of the full vector A must be 1 over p as well. This conclusion is intuitively clear. If the probability is 1 over p regardless of how we choose all other ai, then it is 1 over p overall. There is also a direct proof of this using conditional probabilities. Let epsilon be the event that HA of x is equals to HA of y, and let FB be the event that all coordinates ai for I not equals to j receive a sequence of values b. We will show below that probability of epsilon conditioning on fb, which is equals to 1 over p for all b. It then follows that the probability of epsilon is equals to the summations of the conditional probability of epsilon conditioning on fb times the probability of fb summing for all index b is equals to 1 over p times the summations of the probability of fb summing for all index b is equals to 1 over p. So to conclude the proof, we assume that the values have been chosen arbitrarily from all other coordinates ai, and we consider the probability of selecting aj so that ha of x is equals to ha of y. By rearranging terms, we see that ha of x is equals to ha of y if and only if aj times yj minus xj is equals to the summations of ai times xi minus yi modulo p, summing for all I which is not equals to j. Since the choices for all ai such that I is not equals to j have been fixed, we can view the right-hand side as some fixed quantity m. Also, let us define z equals to yj minus xj. Now it is enough to show that there is exactly one value 0 less than equals to aj less than p that satisfies aj times z equals to m modulo p. Indeed, if this is the case, then there is a probability of exactly 1 over p of choosing this value for aj. So suppose there were two such values, aj and aj prime. Then we would have aj times z equals to aj prime times z modulo p. And so by 13.24, we would have aj equals to aj prime modulo p. But we assumed that aj times aj prime is less than p. And so in fact aj and aj prime would be the same. It follows that there is only one aj in this range. There is only one aj in this range is equals to satisfies modulo p times z is equal to m back through the implications. This means that the probability of choosing aj so that ha of x is equals to ha of y is 1 over p. However we set the other coordinates ai in a. Thus the probability that x and y collide is 1 over p. Thus we have shown that fancy h is a universal class of hash functions.